Hi, I'm Professor John Stone here in the chemistry department at Georgia Southern University. I'm going to give you a very brief overview today of some of the research that's ongoing in my group. So first, I work with nanoparticles in my research group, specifically gold nanoparticles having a rod-like morphology. Let's start with a slide that sort of puts this all in perspective in terms of size scale. Here we have your favorite dog, Rufus, and down here between 1 and roughly 100 nanometers, we're sort of in the nano regime. Nanometers, 1/1000th of a meter, to sort of put that in perspective. And in this regime, we're on sort of a similar or comparable size scale to things like molecules, proteins, antibodies, and bacteria. Many of the things from a biological perspective that we're interested in studying. We can grow these gold nanorods of various lengths or having various aspect ratios. They have a corresponding very interesting optical spectra associated with them, and also very beautiful, brilliant colors, depending on the rod length or aspect ratio. So these particles, when synthesized, have a native positive surface charge associated with them, which allows us to do some very interesting things on their surface. We can coat them with charged polymers, providing functionality that allows us in a secondary or tertiary step to conjugate things to their surface, such as magnetic iron oxide particles, antibodies, or drug molecules, depending on the application need. In this particular project, we have been working on bifunctionalizing the gold nanorods with both iron oxide nanoparticles, rendering them magnetically responsive in the presence of a magnetic field, and also antibodies that allow us to target the antibody, or target rather the nanorod, to a specific site. Here's a TEM micrograph of gold nanorods that have been coated with antibodies. You can clearly see here from the image the more electron-dense, darker material are the gold nanorods, and the less electron-dense material is the material surrounding the gold nanorods. And you see here from this image that it is very specific to the gold nanorod surface. It is certainly associated specifically with the gold nanorod surface. And you don't see a lot of free antibody, or really any free antibody, in the rest of the micrograph image. Once we prepared these bifunctionalized gold nanorods, we of course wanted to make sure they did respond to a magnet. That was the whole reason for conjugating iron oxide particles to the nanorod surface. So we made a little video here of the gold nanorod solution being held against a rare earth magnet. Excuse me. So as you can see, as my student here places the tube containing the bifunctionalized gold nanorods against the rare earth magnet, you can see that the gold nano composite is removed from the tube, or is pulled to the sidewall of the tube within a matter of about 10 seconds. So it's a very rapid, efficient process, again confirming the presence of the iron oxide on the gold nanorod surface. Another project in my group is actually a cancer-driven project. Again, involves the surface functionalization of the gold nanorods. In this particular case, we've functionalized the surface with several components. One of those is an anti-cancer drug, methotrexate. One of those is a photoalabile linker, and one of those is a thermoresponsive polymer. So the general idea here is that the thermoresponsive polymer, when heated, will actually go from sort of an extended conformation to a collapsed conformation, changing the sort of solubility of the overall complex. The photoalabile linker, when irradiated, this linker will cleave the drug molecule from the particle surface, and releasing the drug. And also, you will get some thermal heating as a result of irradiation by near IR light. So you have several sort of pieces coming together here, resulting in a sort of what we hope to be a superior cancer-fighting complex. Thermoresponsive polymer, the controlled external cleavage of an anti-cancer drug, and a cleavable linker that allows release or cleavage under irradiation of that cancer drug. And that's all shown here schematically. And finally, we're also interested in my group at looking at toxicity of gold nanoparticles as a function of their concentration, and then also as a function of their surface capping agents. In other words, what sort of polymer or material we have on the particle surface. And one of the ways that we're doing this is we're using zebrafish as a model. Zebrafish actually provide a very good model for this. And what we're learning about this from this particular study, is that depending on the concentration and the surface coating of the gold nanorods, we see varying degrees of toxicity and malformations in the zebrafish. So you can see at certain concentrations here, the zebrafish growth is altered, is inhibited, and in some cases at higher concentrations, the zebrafish are actually killed. So we're continuing these studies. We're looking to see more, learn more about what sort of surface coatings or how those surface coatings affect the zebrafish, and I hope to learn more about the overall toxicity of these materials under varying conditions. And thank you very much.